Probably the most mind-blowing thing about our universe is just how big it is. It's basically impossible to truly comprehend. But that incredible fact is also kind of a downer, because it means that no matter what amazing things we discover out there, getting to them seems completely, utterly impossible.
So let's put this in perspective. Our closest major galaxy is Andromeda. If we hopped in one of our fastest spacecraft right now, say something zipping along at 28,000 kilometers per hour, it would take us 94.5 billion years to get there. That is more than 6 times the age of the entire universe. The scale of this problem is it's staggering.
And that's the dream, right? It's what fuels so much of our science fiction. You see it in movies like Interstellar, where humanity just pops through a wormhole near Saturn and boom, they're crossing entire galaxies. It's a beautiful idea. But the really wild part, this isn't just made-up movie magic. The concept is actually born from real, honest-to-goodness science.
So today, that's what we're going to do. We're going to dive deep into these cosmic shortcuts. We'll start with just how impossible space travel really is, then get into Einstein's game-changing ideas about space-time itself. From there, we'll look at how a wormhole could actually work, face the pretty big problems they present, and finally, take a peek at what the future of travel might hold.
Okay, let's really try to wrap our heads around this distance to Andromeda. It's about 2.5 million light-years away. So, even if we could somehow build a ship that travels at the speed of light, which is the universe's absolute speed limit, by the way, it would still take us 2.5 million years to get there. I mean, entire civilizations could rise and fall in that time.
So you see, this isn't a problem you can solve with a better engine or more fuel. The problem is space itself. That distance is baked into the very fabric of our universe. So to get around it, you can't just go faster through space. You have to find a way to cheat space. And to do that, you first have to rewrite the rules of the universe.
And the man who did that was, of course, Albert Einstein. His work didn't just adjust our understanding of physics, it completely tore up the old rulebook and gave us a brand new way to see reality. And wouldn't you know it, hidden inside that new framework was the key to our cosmic shortcut.
So, before Einstein, everyone just thought of gravity as this mysterious, invisible force that pulls things together. But Einstein came along with this incredible idea. Gravity isn't a force at all. It's the shape of the universe. He said that big things like stars and planets don't pull on other objects. They actually bend and warp the fabric of space-time around them, and smaller objects are just following those curves.
The easiest way to picture this is to imagine space-time is like a big, stretchy rubber sheet. Now, if you put a heavy bowling ball in the middle, it creates a deep dip, a curve. If you then roll a little marble nearby, it doesn't get pulled by the bowling ball. It just follows the curve in the sheet that the bowling ball made. That's gravity. The heavier the object, the deeper the curve.
He laid all of this out in 1915 in a set of 10 incredibly complicated equations. But you don't really need to understand the math. Just think of them like a recipe. The recipe tells you exactly how a certain amount of mass and energy will bend the space-time around it. And like any good recipe, it turns out you could use it to make more than one thing.
Now, what's really fascinating is that Einstein himself couldn't find all the solutions to his own equations. But as other physicists started playing around with them, they found some really strange stuff. The math didn't just describe the universe we could see, it predicted all sorts of bizarre objects and possibilities that were just hiding in the numbers.
So, the first big solution found in 1916 predicted black holes, these points in space so warped that literally nothing can escape. And for 100 years, that was just a wild theory. But then, in 1935, Einstein and his colleague Nathan Rosen found another solution. This one described a theoretical tunnel, an Einstein-Rosen bridge that could connect two totally different points in spacetime. Today, we have a much cooler name for it, a wormhole.
Okay, the easiest way to visualize this is with a piece of paper. Imagine our universe is this flat sheet, and you want to get from point A to point B. Normally, you'd have to travel all the way across the paper. But what if you could use the third dimension? You could just fold the paper, bringing point A right on top of point B. A wormhole is like taking a pencil and punching it straight through both points, creating a tunnel that's way, way shorter than the original path.
That catchy name, wormhole, actually came a lot later. In 1957, a physicist named John Wheeler came up with a really clever analogy.
He said, imagine a worm on an apple. Instead of crawling all the way around the outside to get to the other side, it could just burrow straight through the middle. It's taking a shortcut through a higher dimension. And yeah, the name wormhole just stuck.
All right, so the theory is beautiful. It makes sense on paper. But how would you actually make one of these things? Or even find one? I mean, to fold space-time like that, you'd need a ridiculous amount of gravity. You'd need an entrance. And just as critical, you'd need a safe way to get out. You'd need an exit.
So according to the theory, the only thing we know of in the universe that has enough gravitational muscle to actually rip a hole in the fabric of space-time is a black hole. Its gravity is so intense that, in principle, it could create the mouth of the wormhole, pulling everything in, including maybe a spaceship.
And this is where we hit a huge roadblock. Because if the entrance is a black hole, a point of no return, then what's on the other side? If it's just another black hole, well, you haven't built a tunnel. You've built a cosmic death trap. You'd just get crushed. For a wormhole to actually work, for you to travel through it, the exit has to be the exact opposite of the entrance. So physicists went back to Einstein's equations. And what did they find? A third bizarre solution, the white hole. It's a perfect time-reversed mirror image of a black hole. While a black hole only lets things in, a white hole would only let things out. It would be this violent fountain, constantly spewing out matter and energy, a boundary of no admission. In theory, it is the perfect exit door for our wormhole.
So now we have the blueprint, right? A black hole entrance connected to a white hole exit. But this is where the hard science gets really tricky, because we've proven black holes exist. We've seen them. White holes, though, they are completely 100% hypothetical. And whether they could even exist is a huge debate in science right now.
The arguments against white holes are pretty strong. For one, they seem to violate a basic law of physics, the second law of thermodynamics. Basically, that law says things in the universe get messier over time, not neater. You can scramble an egg, but you can't unscramble it. A white hole would be like an egg spontaneously unscrambling itself. And, well, we've never ever seen one. But there are arguments for them. Some think they could explain mysteries like the Big Bang, and there was even a weird gamma-ray burst back in 2006 that some scientists thought just might have been a white hole.
But it's so important to remember how science works over time. For more than a century, black holes were just like this, a mathematical curiosity, a weird solution on a piece of paper, total science fiction. It wasn't until 2019 that we finally got a picture of one, proving that this absolutely wild prediction was real all along. The road from pure theory to proven reality can be a very, very long one.
So, while we haven't found a real gravitational wormhole just yet, the story is definitely not over. Scientists are still exploring these ideas, and they're still finding incredible new solutions in Einstein's equations that could, one day, finally get us to the stars.
And believe it or not, theory is turning into reality, just maybe not in the way you'd think. Back in 2015, some scientists actually built a device in a lab that acted like a wormhole, but for a magnetic field. It tunneled the field from one point in space to another, making it seem to disappear in between. Now, you couldn't fly a spaceship through it, but what it did was prove that the basic physics of creating a shortcut tunnel like this is actually possible.
And hey, wormholes aren't the only game in town. There's another wild idea from Einstein's equations called the Alcubierre drive. You probably know it as a warp drive. Instead of punching a tunnel through space-time, the idea here is to surf on space-time. You create a little bubble around your ship, and then you literally shrink the space in front of you and expand the space behind you. The ship itself isn't moving fast at all, the space around it is. It's another theoretically possible but technologically impossible, for now, way to break the light barrier.
The big takeaway from all this is that the laws of physics, as we understand them today, don't actually say no to these cosmic shortcuts. They say it's going to be incredibly, maybe even impossibly difficult, but they don't say it's impossible. And that leaves us with the ultimate question, doesn't it? 100 years from now, maybe 1,000, which one of these amazing ideas will be the one that finally lets us leave our solar system and explore the galaxy?